Hello everyone, and welcome back to another geostatistics tutorial video. And in this video, I want to talk about how we can start to test whether or not our point data sets have one of those distributions that we talked about previously. If you have no idea what I mean when I'm talking about a point distribution, please go back and watch the point distribution video. But in this video, I'm going to assume that we know what we're talking about. And I want to go ahead and talk about how can we test for distributions? How do we have the ability to determine whether or not our data follows some expected distribution, whether we want it to be uniform, whether we want it to be uniform irregular, clustered, or dispersed? So the first thing I want to cover are sort of what we call grid-based methods. I'm going to cover two of those. I'm going to cover uniform patterns let me make that a little cleaner here. I'm going to cover uniform patterns and random patterns. And then in the next video, or in later videos, we'll talk about distance-based methods, which are a little bit more robust and a little bit more nuanced. But ideally, grid-based methods are sort of a good place to start because they really sort of conceptualize the framework of this whole process. So the way a grid-based method works is you divide your pattern. So we're going to use this as our example pattern here. Right? You divide your pattern. So right, divide your area into even spaced grids. Right. So in this case, we have, so these, maybe I can make these a little bit bolder here. Right, so this right here, my handwriting, I cannot trace a line to save my life. Right, this right here, right, this is one grid. So in this case, we have 9 grids. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first thing is going to be to divide your area into evenly spaced grids. The second is going to be to figure out how many points are in each grid. Okay. So you're literally going to count. This grid has 3, this grid has 2, this grid has 2, 2, 3, 2, and so on. 3, figure out the total number of points. Right, so in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So in this case, we have 20 total points. Okay. Step 4, figure out the expected number of points. In a grid. Right, and so this is where you have the different methods, right? Uniform, random, right? This step right here, this is going to depend on the test. Okay, so hopefully that makes sense. Right, this right here is going to depend on the test. And then step 5 is going to be run a chi-square test on the data. And step 6 is going to be analyze results. So if you don't know what a chi-square test is, we're going to talk about that in just a second. We're going to go through an example using this data right here, and we'll explain what a chi-square test is, how it's calculated, and what it shows. Okay, so let's go ahead and give ourselves a little bit of space here, and we're going to use, again, this example here as our basis for our first example. And we're going to test, is this data uniform? Right. So is this pattern evenly distributed? Right. Whether the pattern is regular or irregular, right? Is this data evenly distributed across the data set? Or across the area, I should say. So again, first step, break your thing up into 9 grids. So we have, or break your data up into grids. We have 9 grids. So we're going to say grid, right, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Step 2 is count the number of points. I'm going to call this observed, for the number of observed points. In grid 1, we have 3 points, right? 1, 2, 3. We're just counting the number of points. So grid 1 has 3, grid 2 has 2, grid 3 has 2. So again, 1, 2, 3, 4. Grid 4 has 2. Again, I'm just simply counting the points. 1, 2. Grid 5 has 3. Grid 6 has 2. Grid 7 has 2. Grid 8 has 2. And grid 9 has 2. Okay. So again, all I did for the observed was I counted the number of points, which was step 2. Step 3, get the total number. Right, we add this up, we're going to get that 20 that we talked about before. Right, so that's the total number of points. Now what we need to do is we need to calculate now, again, if we sort of scroll back over for just a second, we need to calculate that expected number of points in the grid, and that depends on the test. Well, for this test in particular, right, we're trying to test, is the data uniform? So what a uniform distribution would look like would be the same number of, like, so let's write that down, right? So in this case, right, our test is uniform distribution. Well, uniform distribution, right, for this to be the case, right, we would expect the same number of points in each grid. Right, that's what it means to be uniform, right? The same number of points in each grid. So, how would we go about determining this? Well, to have the same number of points in each grid, right, this right here would be the same as saying your total divided by the number of grids. So this is going to be 20, right, total points divided by the number of grids. So 20 was our total number of points, and again, 9 grids. I did not make my math easy here, right? 20 divided by 9 is going to be roughly 2.2. Again, I did not make my my math easy on myself here. So 2.2, 2.2, 2.2, 2.2, 2.2, 2.2, 2.2, and 2.2, right? We would expect, again, for a uniform distribution, that each grid would have the same, that should be a 2, not a 9. Right, that each grid would have the same number of points in it. So we've done that, figure out the expected number of each in each grid. So now we have to run the chi-square test. So I'm going to give myself, so we can ignore the grid now. We can go and just look at this data table here. So a chi-square, which is a goodness of fit test. This is a goodness of fit test. Right. Is basically testing, does the observed data match the expected data? That's what the chi-square test is asking. And we'll talk about the null hypothesis here in just a second. So what you do to calculate chi-square, right? The chi-square test statistic is equal to the sum of the observed minus the expected squared divided by the observed. Divided by the expected. Divided by the expected. So observed, right? That's going to be this number here, right? Expected, that's going to be this number here. And then we're dividing it again by this number here for all of the grid cells that we have. And then we're going to sum that up, and that's going to be our chi-square. So let's go ahead and just quickly do this. So I'm going to hopefully have enough room to do O minus E squared divided by E. So if we do 3 minus 0.8, or 3 minus 2.2, we get 0.8. So since these are all going to look the same, I'm just going to do them once. So for the ones that are 3, we get 3 minus 2.2 equals 0.8. 0.8 squared is going to be equal to 0.64. Okay. So we can have a column here called O minus E squared over E. Right? So this is the chi-square for each individual grid cell. And then we divide that by 2.2. And we get approximately 0.291. Right, so this is going to be 0.291. This is going to be, so for the 2 value, it's 2 minus 2.2. That's going to be negative 0.2. When you square a negative, right, it becomes a positive. So 0.2 squared is going to be 0.04. Divide that by the 2.2. And you're going to get approximately 0.018. All right, so this is going to be 0.018. This is going to be 0.018. 0.018. The 3 again is going to be 0.291. 0.018. 0.018, 0.018, and 0.018. Okay. So then this means we have to add all these together, so we're going to sum that. And then if we do the math on that, that's going to be That's going to be approximately 0.709, right? 0.709. Again, adding all these up, approximately 0.709. Okay, so now that we have our chi-square test statistic, right, this 0.79 here, this is our chi-square test statistic. Right, how do we interpret this? Well, as a general rule, right, as a general rule, the lower the statistic, the more likely it is coming from the distribution you want. Right, or put another way, right, the lower this statistic is, the more likely that your observed data matches your expected data. And that kind of makes sense, right? Just look at this equation, right? If O, right, if the observed data is a lot bigger or a lot smaller than the expected, right, this numerator is going to be a big absolute value, right? It's either going to be really large or really, really small, which means that this top number is going to be very big when you divide it. And because you're squaring it, right, even if it's negative, it's still going to be, the absolute value is going to be quite large. So if you have very strong differences from your expected, right, this whole thing here is going to be a much bigger number. So when you sum it, it's going to be a much bigger number, which means your chi-square is going to be a much bigger number. So as a general rule, the smaller your chi-square is, the more likely it is that your observed data matches your expected data. Now, as with all hypothesis testing, right, we can take this a step further and we can do the p-value. So let's give ourselves a little bit of room here. Right, let's talk about the chi-square hypothesis. So what are we actually testing? Well, our H naught, right, our null hypothesis, is that the data matches the expected distribution. Right, this is saying that our observed data matches our expected. So the alternative hypothesis is that the data does not. Right, the data does not match our expected distribution. Right, so this would be traditionally, right, a p-value of less than 0.05 would indicate this, right? A p-value of greater than 0.05 would indicate that we actually do not reject, right? We fail to reject the null hypothesis. So what is our p-value here for this 0.079? Well, calculating the p-value is pretty tricky. It involves a table and some linear interpolation. So I'm just going to skip that math, and I'm going to go right to telling you the p-value for this given application here is going to be roughly 0.998. Right? Our p-value for this application is 0.998, which means we do not reject the null hypothesis, right? We do not reject that the data matches the expected distribution, which basically is a way of saying we think the data may match the expected distribution. Right, we think the data may match the expected distribution, which basically is a way of saying that we think the data is normally distributed or uniformly distributed. And if we scroll back up and go to our little diagram here, right, that makes perfect sense, given that, this looks like it would be uniformly distributed. So hopefully that makes sense. I know there was a lot in this video. I encourage you to pause the video, go back and rewatch parts you're confused about. And as always, please reach out. Thank you.